Good morning, folks. Pleased to be here today. My name is Pete Coates. I'm a research wildlife biologist with the USGS, Western Ecological Research Center. I'd first like to start out by thanking Dr. Kevin Doherty for facilitating this special session, bringing us all together, and getting us all together on the special issue as well. Under this title, Evaluating the Sagebrush Conservation Design Strategy through the Performance of a Sagebrush Indicator Species. We all know what species that is, been obviously one of high attention over the last couple decades. It's not a perfect indicator species. We've seen papers on that, but it's one of the best I think we could all agree that we have out there on understanding the sagebrush ecosystems on how this species performs. I would like to acknowledge my co-authors here, many more on the papers, but particularly Brian Prohaska, who's responsible for a lot of the analyses. So we've seen a lot of figures like this in discussion here. So I'm going to move through this quickly, but there's a myriad of threats in the sagebrush ecosystem: wildfire, grass, positive feedback cycle, expansion of pinyon juniper, anthropogenic development. The list goes on. This is just a few, and it's led to conservation actions across the landscape. And when they're at random, we're putting efforts in areas as an emergency approach, the red areas there. And then when they're within these core areas, they may be much more successful, inexpensive, and effective. And so I'm going to get back to that. And we've seen this over and over in a lot of talks where we've delineated the landscape into these core growth opportunity areas and other rangeland based on some of these threats and the factors influencing sagebrush ecosystem integrity. Our objective here is to see how, in a case study, a specific species, sage grouse, actually relate to this conservation design strategy. First, we're estimating trends within the SEI category, and then, similar to the last talk, taking the responses of sage grouse and predicting those responses based on the underlying factors that make up the Sagebrush Ecosystem Integrity Index. And lastly, kind of uniquely, we're evaluating the conservation actions that have occurred mostly in growth opportunity areas as to whether or not they cause an uplift in these populations, which can be important for understanding how to grow the core. I'm not going to get into the modeling here. I put an equation up for those that like them, but we use a Bayesian state space model approach. And brought together a lot of LEK data from all these Western states. Quite a collaborative effort led by WAFWA and all the state coordinators on coming up with a hierarchical model where we can estimate trends. As most of you know, sage grouse populations are cyclical. They have ups and downs that follow weather patterns where we have high precipitation, growth in populations. But what we see here when we reference in relation to 2022, reference each of these populations, we see greater declines as we move into these other rangeland areas. For example, it's stable, actually slightly increasing, 3% within the core areas, 16% declines within those growth opportunity areas, and 62% declines within the other rangeland. Now, the bottom figure here represents the relative abundance through that time series for each of those categories. And what we see is an actual drop in abundance most substantially within these other rangelands. What this really means is that we're witnessing range contraction. As we lose these sage grouse in these other rangelands, it actually puts more relative abundance within the core because overall abundance is decreasing. What this told us is that the core actually does pretty well at us understanding where stable sage grouse populations are. And I want to point out that there's no political boundary like a state boundary or even ecological boundary like any kind of other type of population boundaries that we've created for sage grouse that predicts so well sage grouse populations at such a large spatial scale. So our next step was to actually take the underlying factors that represent the Sagebrush Ecosystem Integrity Index and see if they could also represent sage grouse population growth. So we modeled that, and we looked at different transformations on those. For example, linear and quadratic effects, and linear effects came out the strongest. Now, it's not surprising in the direction of these effects, but what was really interesting is all of them came out very strong, similar to the way the Sagebrush Ecosystem Index was created. We have the usuals, annual grass, trees, and human modification, all negative effects, whereas sagebrush and perennial grass are positive effects. There's some variation across the different regions. The regions are on the left side there. I'm not going to get into discussion in that variation. There's a lot of that we presented in the paper. But this is unique. We don't have an actual population growth rate model based on covariates at this spatial scale. So it's a novel finding here, but perhaps what's even more novel, we could take those parameter estimates from this model and map a sage grouse centric type of output for population growth using those characteristics. So this is a prediction based on land cover covariates. We think of it like a carrying capacity on the landscape. And we categorize this into high versus medium versus low quality area. And then we could compare that, the sage grouse centric predicted model, to the actual sagebrush ecosystem integrity index and look at agreement between these. And after accounting for random agreement using Cohen's kappa statistic, we found really solid agreement between these two products. Almost nearly perfect in a lot of areas. And where we do have disagreement, we discuss a lot of that in the paper on why that might be the case. We also, before I move on to the last objective, we have a recent publication on hierarchical population modeling and trends related to population clusters. And we looked at those clusters, which are the population level trend in relation to that predicted land cover map, and found some very strong agreement there. That's kind of just the observed trend as opposed to the predicted trend. And where we actually have disagreement in there, it makes sense that there may be issues like predation, disease. Kevin brought up fence collision. Those types of things can be factors that weren't captured within our modeling that might be explaining those differences. And we talk about that in the paper. The last topic I want to cover is whether or not conservation efforts make a difference. It's really important because we've identified that stable populations exist in these core areas. So in these growth opportunity areas, do we have the ability to potentially uplift these populations and over time convert that to core? So similar to what we heard from Tina, we brought in a lot of data from the Conservation Efforts Database and Land Digital Treatment Library, and even brought in data from actual local biologists there out of the district offices to relate in a hierarchical population model whether or not there's some type of uplift using a Bakke design. That's a before-after control impact design. But what's interesting about the bi-state, when we look at that, and we're using the bi-state as the pilot. Right now, we're in the process of doing this range-wide. But when we look at the bi-state, we see similar trends in the long term between the bi-state and the Great Basin, which actually the Great Basin matches very closely to that trends range-wide. It's a 2.9% annual decrease, and the bi-state 2.2, slightly less over that long term. But what's more important is in recent years, since the 1990s, there's 2 orders of magnitude greater declines in the Great Basin than in the bi-state. So a lot has gone on in the bi-state, and just in more recent years, it has not been declining quite as substantially. We think that has a lot to do with the conservation efforts that have taken place there. The bi-state put together a 2012 action plan, funded that plan $45 million, $38 million was spent. Per unit area, the largest proportion of conservation actions probably taken place range-wide, we believe. We looked into weed reduction, PJ removal, sagebrush and meadow restoration, fence modifications, and road closure. Now, we need to lump and split these because we could look at seeding versus planting as splitting, but sometimes we need to lump these if we don't have enough samples from those restoration actions. So there's a degree of that that took place. I don't have a lot of time here, so I'm just going to cover the main result. Basically, when a conservation action takes place, nearly on all occurrences, we had some improvement in that sage grouse populations. This Bakke ratio, the horizontal dashed line, reflects a Bakke ratio of 1, meaning there's no change. If it's above that, there's a outperformance, below it, underperformance. And you could see we use a progressive change Bakke where we're looking at changes through time. And you could see that we get greater performance, outperformance as we increase the time lag out to 9 years. There's a lot of variation among different projects, but overall, a 13.4 4% improvement year over year in the population growth. Now, there's a lot of areas within the bi-state which didn't have conservation action. So how did this improve the region as a whole, or this entire, what we're calling a climate cluster, which is all those populations within the bi-state? And there's a 4.4% uplift in the bi-state as a whole. Now, thinking about the math there, I showed the previous slide, and the most recent decline, if we're thinking about scales, the last 10 years, has actually been 5% decline in the Great Basin. And we've had a 4.4% uplift in the bi-state. So what this suggests is that the conservation actions have actually improved the bi-state to decouple it from what's gone on in the Great Basin and those declining trends, a 37.4% increase. An example here, for example, seeding and planting, we have these for every single conservation action, but we see more improvement from planting than we do from seeding. I'm going to move on here because we're almost out of time, but the take-home points here is the sagebrush ecosystem integrity index is ecologically relevant to this indicator species. And what this means is when we protect the core, we're protecting stable sage grouse populations. It's an inexpensive, highly effective approach to devote energy into that type of a strategy. The growth opportunity areas, though, provide some potential for uplifting these populations and even converting that to core and reversing these long-term declines. There's a lot of variation in the success of these projects. We only had one mechanical treatment of weeds that was not quite successful, but with longer periods of time, it might be. But the biggest bang for the buck came from sagebrush restoration and conifer removal. Conifer removal was the most carried out application there. And we're hoping with range-wide data, and this analysis carried out range-wide, longer time frames, more samples, we could really delineate out the variation and understand, kind of prescribe a recipe for how to actually do the conservation action in a specific area that's going to have the most benefit for sage grouse. So as Kevin pointed out in the first talk, the SEI really does provide, or this conservation design, a spatial targeting, but understanding something about the effectiveness of the actions provides us more of what to do once we understand where to go. And so this really contributes to that aspect. I want to thank everybody, a lot of folks involved in the research, particularly all the state coordinators listed there on the left side, and the Fish and Wildlife Service for funding this research. Thank you.